So welcome to the afternoon session, and our speaker is
Wojciech here.
Wojciech Kaminski, talking about conformal Einstein.
So originally, I wanted to talk about near horizon geometries, but then there were so many excellent talks that I decided that it would be not so good. So I changed the topic to this conformal Einstein equation. But apparently there were also several talks about the things that, but okay, I didn't know that, so it's done. Okay, so maybe what will be the topic of this talk? So let's consider solution, okay, Einstein equations in d dimensions, but with the positive cosmological constant. So this is the simpler case than 0 or negative cosmological constant, but it's okay. So the method that I will be presenting is also can also work in this more general in some cases. And we are interested in the question about asymptotic simplicity of the solution. So what does it mean? It means that our physical manifold is a subset of some bigger M bar. And the metric, so this physical metric, when we rescale it by some factor, it extends smoothly through this boundary. And so we are assuming that the boundary, so this conformal boundary is exactly the place when this omega vanish. So one can check that with this assumption that lambda is bigger than 0, this set is always space like it has a lot of interesting properties. I think Roth was the person who described them or discovered. So, but we want assumption that this boundary is a Cauchy surface. Of course, this is a bit oversimplification. It might be several Cauchy surfaces, but let's assume that if we take part of that, it will be a Cauchy. And what is interesting? So, for example, interesting is a fact that there is difference between even and odd dimensions. So for the even dimensions, such solutions are in the sense generic. This means that if we make the small perturbations, we'll have this smooth behavior at the sky, or maybe not at the boundary. But for odd, so one can check that if one expand metric along the boundary, then it turns out that one need to also incorporate some logarithms. So it means that in the odd dimensions, it's not generic. In some sense, it's a difference. And so I would like to explain this fact in geometric way. So of course, we had already on this workshop that there is a method to deal with that. So this method was invented in the 80s by Friedrich. And it consists of the following idea. So suppose that we found some new set of equations such that every solution to Einstein equation is also a solution to this new set. It's like more general equations. But we assume that this new system is conformal invariant. So it means that if we rescale the metric, it will still be the solutions of this new equation. And we want that this new system is hyperbolic, of course, after imposing the gauge. Because so it's like Einstein equations are not hyperbolic, but they're hyperbolic, let's say, in the, for example, harmonic gauge. So here we also need to impose gauge, but this gauge, of course, it needs to be more, because not only diffeomorphisms need to be gauge fixed, but also we need to impose some condition on the scale. And additionally, we want that the scale factor also can be propagated. So once we know it on the initial surface, we can propagate it in the future. And let's say maybe it's a bit vague statement that property of being Einstein metric property. Okay, so if we find such set of solutions, and Friedrich found it, then we can understand stability of the system. There are many properties of these asymptotically simple solutions by some very basic properties of hyperbolic systems of only well-posedness. So what are these properties of, so if we have nice hyperbolic equations, then we know that we can develop, so if we have some initial data, we can develop this equation for some small neighborhood of this initial Cauchy surface. Moreover, we know that this development is depending continuously on the initial data. So if we change a bit initial data, then this development change also on a bit. Of course, one need to somehow measure what a bit means, but usually in some Sobolev spaces or things like that. Okay, and so also I added, this is not the proper well-posited, but we also have some other nice properties of this hyperbolic equation, like propagation with finite speed, that sometimes are useful in the study this equation, because we can do everything locally. So we don't need to care about global properties of Cauchy surface, only local. Okay, so how from these properties stability of de Sitter follows? And this is very simple argument. That's why I will maybe tell about it. So point is, so let's consider de Sitter, for example. So de Sitter after a conformal compactification is turning out into something called Einstein universe. And this Einstein universe has this dark blue, okay, darker blue part that is the physical space, the boundaries of future and past Cauchy surface, and non-physical part. Okay, so now if we have some Cauchy surface here and we perturb a bit the initial data. So what happens? Of course, we cannot expect that singularities will not form. So they can form, but if this perturbation is small enough, they will form in this unphysical part of the space, of this non-physical space. Okay, so but then it means that the physical part will be untouched in some sense. So of course it will be a bit different, but it still will have this conformal boundary. Everything will be smooth. Okay, so and this argument is just showing stability of the system. So this is the Friedrich proof. Okay, so what is the point of my talk? So this Friedrich equation. So they were written, I think, yesterday. I think whole system, except maybe omega. Omega was not. So there were these. Okay, maybe it's my personal. They are complicated. So they are. This is first order system, and it's based on some special property of the Bianchi identities in 4D. So if one would like proceed like Friedrich, it would not. One cannot in easy way generalize it to high dimensions, and so maybe the comments, of course. So this first order, they're nice, but one can also rewrite it as a system of quasi-linear wave equation. I think Paetz did it some moment. So you just prolong it a bit and you have it. Okay. So, and yes?
This is a quasi-linear system for which variables? For
okay.
metric only.
No. So this system is for the, so it's for the metric, connection. I think there is also coming the let's say Schouten and Weiltensor. So it's many variables. Yes.
So in that's
no. So he just took. If I remember correct, he just took this system of Friedrich, and so he got equation for the same variable. So it is also many variables, yes, but some of these equations you can just, I think, cancel. So I expect, but I'm not sure. I expect that the system that I will be 2 slides later showing is equivalent to Friedrich, but I'm not sure. So one would need to, no, it's complicated. Okay. So to understand why, so my talk will be based on some, let's say, property that if one don't pay attention, it's easy to overlook. So let's look for two examples of something that one could expect to be hyperbolic system. And this first one is like the most basic example that everyone knows of a quasi-linear wave equation. So this is something that the leading order, so the highest derivatives is given by this box dot. So this box dot is something like the Lambertian, but in coordinates, acting on the field. So this metric can depend on the field. This U might be sometimes so. And there is plus some lower order terms that I usually will denote by 3 dots. Okay. And this is known example. For example, Einstein equation harmonic gauge, they is in this form, and this is used. It was used as the first proof of well-posed Einstein equation. Okay, but then one think, oh, so maybe things like that. So suppose that the leading order, so the highest derivative, it's not box on U, but some powers of box. So that maybe also should be. So if one, for example, look at the Cauchy-Kowalewska theorem, you will not notice difference. You can just expand it and you can compute order by order solution. However, this equation is typically not hyperbolic. And I gave here examples. So if it's not hyperbolic, one can also expect that things like that will not be hyperbolic, even with the constant coefficients and linear. And in fact, one can find examples, many examples, so this is one of them. So suppose that we have an equation like that. So one can compute modes expansion, and one can notice that all the modes are bounded. So that basically you can, by Fourier transform, you can write the solution explicitly, and it's well posed. However, if one changes the sign here, this is lower derivative. Yes, so this is the third derivative. So this is this leading term, and this is these 3 dots or F. So if one change here, then it turns out that the modes are growing. Of course, if they would be just growing, it also would not be a problem. But if you higher mode you take, they're growing faster and faster. And this is already a disaster. And one can show that there are some nice smooth functions that does not have a development at all. Like yeah, so yes, but not as extreme. But yeah, but yeah, I think it's a good comparison. It's a bit milder, but enough. Okay, so in principle, one would need to look at the many lower order terms. So if here would be some lower powers, then one can show that it's okay. But this is complicated. Okay, so if one think about so maybe this is to. I would like that you have in mind these two differences. Okay, so if one think about this requirement of Friedrich, so what is the natural equation that everyone knows that is satisfied is if the Einstein equations are satisfied. So in 4 dimensions, Bach equation. So Bach tensor vanish if the metric is Einstein. Okay, and so there is Lagrangian for this Bach equation. It's given by the square of Weil. That's why I think sometimes it's called Weil gravity. So and because of this gauge invariant, this conformal invariant Lagrangian, this Bach tensor in 4 dimensions has this nice property, conformal rescaling, and that means that equation Bach equal to 0 is conformal invariant. So it's a candidate for this Friedrich type system. Of course, if one can show that it has well-posed initial value problem. Okay, so let's look whether it has this well-posed. Of course, it has a few nice properties that's coming also from this Lagrangian. It's like Einstein equation, divergence is 0. We are quite happy with that, and also tracing. Okay. Maybe I want. Yeah. Yes. Okay. So one need to impose some gauge conditions, and so the natural choice. So, and I don't know who invented it. It should be this one, but I think maybe Anderson or Wojciech. So then that, of course, one of the choice would be like in the Shoko-Dubois method that we impose in harmonic gauge. And the second choice would be that the Ricci scalar is 0. So this can be always achieved at least locally by solving the equations for the coordinates. And this is Yamabe equation, but in Lorentzian signature, it's a wave equation, so one can solve. Okay, and if one look how our back tensor, what is the form of back tensor in this guy, is equal to the, I would call the gauge back tensor that has the form that is this box square plus lower order terms. Okay, so is it well posed? Is hyperbolic? Yeah, of course. Yeah, that's exactly. And okay, so for Bach, maybe one could some analyze these lower order terms, but looking complicated. But maybe let's look again at this formula for the Bach tensor. Yeah? So if we look at that, so we notice that there is some nice way of rewriting this equation as a system. So, of course, let's introduce new variable. Let's call it P prime, that we hope will be a Schouten tensor P. So P is the Schouten tensor, and the back is something like that. And in this gauge, this P can be written as a box of G plus some lower order terms. So we can rewrite this equation in this way. And so now we have a system of two wave equations. So we have here a box on P, and here we have box on G. So we have two variables, and we have some lower order terms. So these three dots are terms a bit similar to this, but I distinguish this C for some reason. So is it hyperbolic? Is it a quasi-linear wave equation? No, it's not. This C depends on the second. Okay, so probably my question was bad because I didn't say what is C, but C is a while. So while depends on the second derivatives of the metric, so it's not good. So it's still not. It's not linear wave equation. So it's looking that we didn't gain much by writing it in this system form. Okay, so what we can do if we, so is it visible that it's red? Yeah, probably yes. Barely, but it's okay, it's at least visible. Okay, so what we can do, so, and this is coming something that I learned that probably Leray invented this method in 50s, and it has some lecture notes, but somehow it's not widely known method, but probably used extensively. So what we do, we just introduce new variable. Okay, so let's differentiate this last equation overall and introduce new variable that we hope will be this derivative of the metric. So if we do that, then suddenly this system, now it's a system of three equations, turn out to be quasi-linear. Why? Because in this C is the second derivative of the, depend on second derivative of the metric, but now it will be first derivative of our new variable. Okay, so we have a linear, quasi-linear wave equation, And one can show that solution to this equation with the good initial data that this A is related to the jet of metric. It will also be all the time this jet. So one can show that if this system is well posed, also origin equation is well posed. Okay, so maybe I summarize what kind of system we can deal with this linear method. So we can have system of many, let's say many tensors. This U are some tensors. And instead of standard quasi-linear term, like at the beginning, we can also add that this F, so this remainder, depend on the second derivatives of the field, but only of the fields of lower index. Okay, so it's something like a quasi-diagonal system. Okay, and this is also will be well posed. So I added here additional so I will call this generalized quasi-linear wave equation. I added this recursive because we want that the, let's say, first tensor is determined by the zeroth tensor. So this equation should be such that you can, let's say, for n+1, you can solve and you can iteratively put it in this system and obtain some single equation for U0 that will be of the high order terms. And this equation also will be well posed. So we have some, let's say theory how to deal with some subclass of these systems that can be reduced to such equation. Okay, and now let's look at this. Our Bach, it's like that. Yes, so this gauge fixed Bach equation is a generalized. Okay, so of course it's still not showing that we can use this Bach equation for the development. Yes, because problem is that we have gauge fixed equation, so we even don't know. First of all, we don't know if B is 0. We don't know if P prime is Schouten. So unless the gauge conditions are satisfied, so we need to show that gauge also propagates. So it's standard method of Schoeppe-Brouwer. Of course. So how this method is working? We're looking at the dependencies between equations, like Bianchi identities and so on. And from then we can derive some auxiliary hyperbolic system for this gauge function. Okay, and then if on initial surface these gauge functions vanish, so this initial data for this gauge function is usually the gauge conditions for the initial data plus constraints. In this way, constraints enter the Schoeppe-Brouwer method. So if this is satisfied, it will be satisfied everywhere, and we are done. So we solve the problem. Okay, so I gave version of this talk earlier, and always everyone was complaining that it's complicated. So that's why I wanted to give a simple example that will be understandable, but I don't know whether I achieved my goal or not. Okay, but let's look. So we can write these gauge fixed equations as let's say non-gauge fixed of plus reminder. So this reminder, of course, it's a function of gauge. Okay, we can write it as a linear function of this gauge function, linear functions of the gauge function. So they vanish if the gauge is 0. Otherwise, they adding something to them. Okay, and now let's looking for this identity. So here, what we have, we know that the Bach tensor is divergence free. We know that it's these traits vanish. And we additionally know that the Einstein tensor is divergence. So this is, okay, so we can just take this equation. So we look at what we have. And if one do that, so one take divergence of the first, then we obtain some equations for, let's say, this function f and p prime. So f is our harmonic gauge function. P prime is a trace of this would-be Schouten. So trace of Schouten is basically trace of Ricci, so the same gauge. Yes, so the P prime should be, we expect, okay, we hope it will be 0. But if one write this equation, so we have three conditions, we're getting three equations and they are appearing additional function. So it's not the equation only for this original function f, nu, so harmonic gauge, this p prime, but also there is additional strange function. So my hope was that you will feel confused now. And the second hope is that I will manage to deconfuse you in the next. So it seems very ad hoc. And okay, this Einstein condition, so it's okay, one can use some abstract arguments. So one, for example, knows that if you have this development, let's say for the Bach tensor and for the Einstein tensor, then you can compare them. So you know that development for Einstein tensor is also for the Bach tensor development, yes, because its Bach is 0. So you can compare and you can notice that because one extends to the boundary, the second also extends. But okay, it's okay, and so how to make it less confusing? I think it's becoming less confusing if you go to higher dimension. That rarely happens, but I think in this case it is like that. So what is the generalization of this Bach equal to 0 to higher dimension? And it turned out, okay, for many respects, it's the Pfefferman-Graham tensor generalization, and also for this equation. So there is some, I will in bad way define it in the moment, this Pfefferman-Graham, but it's basically some special tensor that has this form that the leading term is box, so the Laplacian, the Lambertian, to some high power on the Bach tensor plus some lower order terms. Okay, and also it has conformally invariant Lagrangian. Actually, this Lagrangian, I think it's not known. So one knows Lagrangians for the Pfefferman-Graham tensor, but they are not conformally invariant. So there are like one can take holographic volume or Q curvature, but there also exists conformally invariant Lagrange. And this is only given by some theorem by Alexakis that showing that that we can write, let's say, holographic volume or Q curvature as something proportional to Euler term, conformal invariant plus total divergence. And of course, from the point of view of Lagrangian theory, this Euler and total divergence we can just cancel, and we get into this something conformal invariant. But I think it's not written probably in dimensions higher than. Sorry. No, box, yes, I didn't define it. I forgot to define it. It's just the Lambertian. It's under the Lambertian. But no, it's yes, it's covered. It's okay. Okay, so so what is Laplacian acting on tensor is just covariant derivative, and you contract in this. So it's not on component. Of course, if you look at the leading term, it's second derivative there. Yeah, but so it's okay. No, no. Okay, so
Yeah.
It's a tensor, you can act, yes. But okay, so this is the proposition, and maybe I will very ugly way explain Pfefferman-Graham construct, but in an ugly way. So of course there is nice way if you so it's natural construction associating conformal class of a metric, a pseudo-Riemannian manifold in dimension higher by 2, and the signature is changing by 1, 1. So for example, for the Lorentzian, this ambient metric will be in signature 2D plus 1. Okay, but for this application, it's important to know this somehow in specific coordinate system. And this coordinate system was already appearing today twice. It's the null-Gauss or Moncrief coordinate system. And assumption about this metric is that there is a homothetic killing vector. So this killing vector is just its action is rescaling with respect to rescaling of t. And additionally, we are assuming that the Ricci tensor of this ambient metric vanishing to the high order. So this order, okay, for us, fortunately, in the even dimensions, you can only assume that this Ricci vanish to the order d plus 2 minus 1. This plus means that also the trace of the Ricci vanish in this highest order, but this is not important for this. Okay, and if one assume these conditions, and also, so this n, it's a natural, natural object, it's a bundle of scales for the original metric. So we want that this g tilde, that is some function. So we can think about this g tilde, this part of this our metric, as a row-dependent metric on our manifold. In this case, will be our spacetime, or even this m bar. And we can expand it in a row. And this expansion is determined by this condition for of course, it's determined only to specific order. We cannot determine beyond. Okay. And what is also important, if one counts how many identities you have from this vanishing of the Ricci tensor, of course, there is too many conditions. However, some of them are automatically satisfied. This one in the direction t. So this direction t I denote by 0. And we are left with the 3 parts of this Ricci tensor. And there are between them again some dependencies coming from Bianchi identity. Okay. And what is the definition of the abstraction tensor? The definition, like the name suggests, whether we can extend to the Ricci flat or not. And since there is at the order d by 2 minus 1, if we expand this R mu nu, then till this order it will be 0. At this order we can have something non-zero. And if one look carefully, so this recursive determination, it's providing so G1 will be higher order, so it will be already the second order of the metric. G2 will be 4th order, and so on and so on. So this ambiguity tensor is very high order. So maybe what I wanted and I didn't told that, so if one seeing such nice object but high order, one can think of why don't you use something depending on the lower derivative? Maybe there's something better. And the claim is no, there cannot be something better, because if one look at the conformal boundary at the initial data, then one notice that this initial data is let's say, so up to gauge. So this is the metric restricted to this sigma. So sigma is boundary. And then, like many derivatives of this metric inside the bulk, inside our physical manifold are determined. And only the next non-trivial piece of the initial data appearing at the d minus first derivative in direction of So equations that are of lower order, the D, cannot serve for this purpose. So okay. So okay, depending on this derivative. So now explanation. And so let's us, of course, the best would be to look at this. They are quite ugly, so I didn't put them, this equation, in the whole glory. But it's turned out that, okay, so one can look, for example, at the first order. And in the first order, one notice that this G1 is just the Schouten tensor. So this is the first. Now, second order will be something like back tensor, but then it's starting to be messy. So maybe to make it a bit better, one, instead of using this S union, typically, like if you look at the Pfefferman-Graham book, they, in order to determine this metric, they're using this S union, only this tangent to M part of the Ricci tensor, this ambient Ricci tensor. But in practice, one can use any combination, and one can take such strange combination. So the notation is that, of course, we're dealing here with the Taylor series. So let's denote the integration by this inverse of the derivative. So it's on the Taylor series, it has well-defined action. Yeah, so it's nth term rho to n. It's changing into rho to n plus 1 divided by n plus so on. Okay, and if one takes such nice combination, and if one knows Schocker-Brouwer method, one sees something in this, but okay. So if one takes this combination, then one notices that for n bigger equal to, these equations, they simplify considerably. So this original, they were not so simple, but if you take this strange combination, one getting equations like that. So these three dots, they are depending on the, they may depend on the second derivatives, but a lower order matrix, and some first order derivatives. Okay, so this looking already very good. If we remember how this generalized quasi-linear systems will look. Okay, but we're missing two pieces, n equal 1 and equal to 0. And it's not surprising that we're missing them, because we know that this equation, this Pfefferman-Graham equal to 0, it has some gauge transform, gauge freedom. Yes, so it cannot be hyperbolic. It would be a contradiction. Yes, so we need to make some gauge fixing. And this gauge fixing is the following. So we need to a bit massage this function gamma and g by adding these terms that previously they were written also in red as S1, F1, and F2. Okay, and then if we this star denoting the gauge fixed version of this equation, then they actually form the generalized hyperbolic system. Okay, and so if one look carefully, so now we see that we have these gauge functions, and so maybe one more thing, there is some nice feature of these equations. So we're looking at this expansion of the metric, and we notice that this system is some moment decoupled. Yes, so normally it's coupled to n plus 1, but if one take n equal d by 2 minus 1, then suddenly this term drops, and we have, so it's somehow decoupled. So we have like this system of equation, they hold, let's say, arbitrary if these en are satisfied, but they decouple this first d by 2 terms. So they are forming the closed system. This is this generalized hyperbolic system that can be used for the well-posedness of the Pfefferman-Graham equation. Okay, but we have the same problem as for a Bach tensor. So we need to know whether whether the gauge functions also propagate by some hyperbolic system, because if they would not, we would only solve this initial problem. And okay, so if the gauge conditions are not satisfied, we are not solving the original equation. Okay, so but if one look at the, so previously we needed to look at some unrelated equations. So one was the divergence of the Bach, trace of Bach, and divergence of the Einstein tensor. But now it turned out that all of them form various parts of the one Bianchi identity for the Einstein tensor in the ambient space. So they're somehow unified. And that's why I claim that is explanation simplifying. So you may also think otherwise, but okay. And maybe one more comment. So this first two, so of course we also need to expand these gauge functions into series. And the 0th order terms, they are now these original gauge conditions. But the system is not only for these two functions, but it's also for some, let's say, something I would call the higher gauge functions that are in the ambient metric, they are identically 0. But of course, this is okay, because if we show that they evolve by hyperbolic system and vanishing initially, then they will be 0 everywhere, and we are in the ambient construction. Okay, the same way as previously, the vanishing of this initial data for this system follow from the constraints. Of course, if we need to assume that our initial data for the metric, that is quite high order derivatives, that it's satisfied, that it's in the proper gauge, yes? So this is one condition, but second condition is the constraint equation. So the same way as for the Schocker-Brouwer method, that is not surprising, because somehow it is just original Schocker-Brouwer method, but in the ambient space. Okay. So maybe the last 15 minutes, yes, I will spend on something that will show that this way of thinking, so that in fact we're looking for the, so maybe I will explain why I think this is nice, because in some sense, whatever you know from gravity, or let's say from propagation, like mathematical relativity, like properties of propagation of some objects, you can just translate them to the ambient metric. I hope that they will provide you this generalized system, and you can use it. So this generalized system will be conformal invariant, and you can use this system to make some new statement in the conformal world. Okay. So maybe let's look at the Einstein conditions. So metric satisfies Einstein equation if and only if this G tilde, so this part, this ambient metric, this non-trivial part in the ambient metric is of this form. And this property is equivalent to some property of, let's say, some function that he is written. I think I don't know who first find this. I think it's quite old result that is of this form. It's not okay, but so this O need to satisfy the second derivative is 0, covariant derivative, and this means that the, let's say, gradient of this O is a killing. So yeah, it's like that. In fact, it's somehow related to the Kotler matrix. But okay. So of course, our problem is that we don't have. So I wrote that G is of this form, but we don't determine the whole metric. Yes, so we only determined up to order d by 2. So if we change this metric at this higher order, this condition will not longer be true completely, but it will be true with some reminder. Okay, and there's also, if we change the conformal scale, then this Einstein scale, so this omega, will be related to this O by this formula. So it's the just value at rho equal to 0 and t equal. Okay, so so we come to such conditions. So it's and who invented this condition? You invented? No.
Almost Einstein.
Yes.
Well, I think it was Hildebrand who linearized this conformal to Einstein.
Okay.
Thing. And then we've sort of popularized, including the zero locus.
Okay. Yeah. Okay. So this, and so I will work with this condition. Okay. So of course the point is that if O is 0, so omega vanish. So then this condition is still okay. So it's describing the boundary of our physical space, but nothing is wrong with this condition. That does not fill this boundary, and it's equivalent. So I wrote it in the ambient space for the reason that I will be using this, but it's equivalent to some condition for the omega. Okay, and how to determine? So if we have omega, how to determine this O? We just extend it by the harmonic extension. And of course, I cheated here, but I will not tell you. Okay, so now what I was telling that if we have this, if we can do something in gravity, then we can also do it in this ambient space. Okay, so hope is that we can do it in ambient space. So how to show propagation of the killing vector? So suppose that you have initial data in GR, and you know that this initial data has a killing vector. So how to show that the whole development will have killing vector? Of course, there might be some abstract argument, but if you want to show it by the hyperbolic system, there is a way. And the way is the following. So you show something that sometimes is called propagation identities. So suppose that we looking for the twist-free killing. I think that's I hope the correct name. So the killing that is given by the gradient of some function. Okay, so need to satisfy this formula that the second derivative of this function is 0. Okay, and of course, if this formula, if this condition is satisfied, also f is, I would not say okay, satisfy the wave equation. Okay, so we can use this later equation to propagate it to the whole spacetime, and this would be the candidate for the f, extended f. Only we need to show that indeed this f satisfy this killing equation. So how to do that? So let's concentrate on this state when the Einstein tensor vanish. One can show such identity. So this identity is telling that if some function f satisfies wave equation, then the second derivative of this function satisfies also some kind of wave equation with some reminder. This reminder has the second, has some Ricci Riemann tensor, but for us it's 3 dots. So some, okay, so, but then if this second derivative vanish on the initial surface, by property of the hyperbolic equation will vanish everywhere. And okay, we are done. We showed that gradient f is a killing. And so we just extend f by the wave equation, and the second equation showing us that it's a killing. Okay, so we can do the same in the ambient space. Okay, so this condition that our function O will be satisfying wave equation, will be harmonic, is equivalent to such such equations. And in fact, one can check that this equation, okay, if one expands, so there is this Laplacian, this D'Alembertian, but one can again expand it in rho and show that this forming the generalized linear wave equation. So they also decouple. So this Cn is equal to 0 for n equal d by 2. So it's providing us equations only for this d by 2 plus 1 first time. So from 0 till d by 2. Okay. So then one can, from this other equation that I was denoted by this crossed box, so one can also provide, so one can also write it in the ambient space. And if one do that, one also will obtain some system of generalized wave equations. Okay, so that's very good. And also linear, because it seems that our method works. It's just enough to extend, let's say, this O, so omega, using the wave equation, this generalized wave equation to the whole space-time. Okay, and then applying this identity to show that also the property of being almost Einstein is satisfied. Okay. Okay, so this was to check whether anyone looking at the indices that are written here. Everyone who knows very well the ambient metric. So if one remembers, so okay, this is something bad. So something wrong with these indices. Yeah, so we need to have, we need to have this metric, this Ricci, vanishing to higher order that we have in our ambient construction. Okay, and if one look, if this equation, let's say for O, or this equation for this D, that D will be this condition of almost Einstein, they also depend on the higher order of the ambient metric that we determine. So it's not good. However, it's not so bad as you may think, because at least in Lorentzian signature, we can always extend the metric to the higher order. So so there is some natural class of the extension. It's not important. So but these are these polylogarithmic ambient metrics. But for us, it's not so important how they are exactly constructed, but they depend on one additional tensor. So once we provide this tensor, we can construct an extension to arbitrary order. So typically, it will be not Ricci flat. However, if the Pfefferman-Graham tensor vanish, and this A, divergence of this A is traceless. And divergence of this A satisfies some condition. This D is some complicated tensor. So, but if it satisfies this condition, then the extensions themselves are Ricci flat. So typically, so they are constructed as a smooth part of the Ricci flat polylogarithmic extension. So this smooth part usually is not Ricci flat, but in this case it is. And on the globally hyperbolic spacetime, such A always exists. Of course, it's not unique. So there are usually, okay, it's many of them. However, so we can use one of them to propagate our omega. Let's choose one. We propagate, and this complicated system of many equations that were coming from the wave equation in the ambient space, it's if one recursively reduce them, one obtains something that is usually, so it's not critical GJMS operator. The one that is well-defined is supercritical. The one that is not well-defined, however, we adding this additional piece of data, and okay, this is allowing us to define also supercritical GJMS operators, and this equation is well posed. Okay, so if this AU is Ricci flat, of course, then it's Ricci flat to infinite order. Then this identity holds. So we can use it to show that also this second system, the system that propagates a condition of being almost Einstein, is also its holds. It's also global. It's also a generalized hyperbolic quasi-linear wave equation. So it allows us to show that if on it holds on initial surface, it will holds everywhere. Okay, and so it turned out that this condition for this second system for initial data for the second system to be 0 is exactly condition for the standard that omega is determining the Einstein almost Einstein structure on the surface. So it's only this D is the jets. So it's only D minus first jets on the surface. If we know that initial data is 0. So by propagation, we know 0. Okay. And though it's looking very strange because there is a choice. Yeah? So we're choosing some A for propagating this omega. So what happens if we choose another A? And this happens something very funny. It turned out that, of course, this P is depend on A. So typically, if we have solution of P for one A and P with other A, they will be different. However, if the solution additionally defining almost Einstein structure, then this omega satisfying this PA for any A. So that means that we can use any A for the development of omega, and whatever A we choose, it will give the same result. But this we know only after. So once we know that it's the almost Einstein structure, we check that we can use any. Okay. So my hope is that I will at least convince you that in this case, using the ambient metric simplifies things. So at least making it like direct counterpart of the standard Schoke-Brouwer method. So if someone knows Schoke-Brouwer method, one just look at the ambient space. One need to make a bit of tries, but if one do it properly, one getting the well-posedness for the Pfefferman-Graham tensor that otherwise would be, okay, for Bach tensor, one can guess it, but for higher order tensor, like for higher dimensions, probably not tractable by the direct method, yes? Okay, and so maybe, so this was supposed to be teaser for Jurek's lecture, but unfortunately, so I will only tell that one can play this game a bit further. So one can also look for the, okay, so now we have two field theories that are somehow related. So we have this field theory for the Pfefferman-Graham tensor, and we have field theory for the Einstein equation. So what is the relation between them? And it turned out that there is relation. So for example, if one want to compute the symplectic form, it turned out that for the non-zero cosmological constant, the symplectic form that one would obtain, so symplectic potential that one obtain from the standard Lagrangian for Pfefferman-Graham, this non-conformal Lagrangian, the holomorphic volume, for this Lagrangian, one getting something that is proportional to the symplectic form for the gravity. And this is true in any dimension. And so there is relation, and in 4 dimension, one can use this relation to somehow renormalize this symplectic form and obtain some properties of the charges on the ground value, but I will not tell about it.
Okay, thank you very much.
my memory from the 4D case is that
for the okay.
yeah, the 4D case is that the government is non-zero. The power squared actually is a good proxy for the Einstein.
Oh yeah, yeah. So
but as lambda goes to zero, so you end up with zero. So all the charge expansion.
Yes, yes. So
Einstein gravity from conformal gravity.
yeah, so
See that, anyway, that's all.
yeah, so
I'm not saying.
So of course, to analyze the properties of the solutions, I think this conformal gravity it's also working, so it's okay. But you're right. So when this let's say this presymplectic potential for this conformal, okay, this Pfefferman-Graham is equal. So there is some constant, but there is lambda, I think, dimension by 2. Times yeah, so of course yes, in the null, yes. Then you can, and we feel like we somehow use this because so this is not determined uniquely. Yes, so depend on Lagrangian, and also it's up to some total divergence. Yes, so you can add to this presymplectic potential, you can add something. And if yes, yes. So okay, so but which one you mean? Yes, so this logarithm in odd dimension, they're showing that you cannot use this method. So there is no chance to have the hyperbolic system that propagates. Because if you would have hyperbolic system, it would propagate through the boundary. There's no reason why logarithms should form them. So here you have smooth data, they propagate to something smooth. Now, of course, up to singularity, but singularity is further. So there is no chance to have the hyperbolic. So this Friedrich method for odd dimension will not work. Of course, you can think why on the null it's no problem, but on the null you have something propagating along the null surface. So then, of course, might be something from the I0 coming. But on the future slide, there is no. So one know that it's only can work in even dimensions, and it need to be of this high order. So, yeah, so okay, I know what. So I don't know, but yeah, okay. I will not say anything clever in this moment. So I will not say anything.
Seem like a very
Yeah, so I think but it was not okay. So you can get them, but this. Okay, I don't remember, but I think it's more was so because it's related to this work with scattering of. So I think. I'm not sure that it will work in the Lorentzian signature, but I'm not sure. And of course, so one can get, let's say, this kind of operators, but something like analytic extension. So you can, dimensional analytic continuation. So, but okay. I don't know.
What else? No. So let's take the speaker again.